Hey guys, I thought I would come along and try and clean up some of these problems we've been having with these questions. It was really interesting today to see the different ways we approached it. I've had a read about circuits, I've learnt something today, and I thought I would just try and clean up any of the questions people may still have in their minds. Turns out both ways, all ways we were trying to do the problem, we're all working fine. We just need to be sure we're clear in our heads when we're doing it exactly what we're doing. But first, the Gallopin-Gertie oscillating function, so waves happening. What happens if they are not damped? Here's an example of what happens when they're not damped. Enjoy. It was built in the corner of Washington to realize the dream of man. A dream that meant they would twist some steel between two shores of sand. Out of all the bridges in the whole Northwest, it would be the greatest span. And then the wind came, the storm brewed, and blew that bridge around. And when the mighty tide came for its gust of strength, it plunged into the Puget Sound. Pretty classy, right? I don't want to spoil all the fun. You can watch as I sort of preview through there. It does a nice little dance, dancing along with the music. And if we get to somewhere closer to here, I think you'll see some more action happening shortly. Let's see. Wow, that's pretty scary, isn't it? Only been open for about 4 months at the time, I think I read somewhere. So you could see the oscillating function just from the wind. Just a little bit of wind was enough to get it bouncing up and down like that. And eventually, because it wasn't damp, because there was nothing built into the construction of the bridge at those times, they weren't aware that the wind would be that powerful and have that effect. Disastrous results. So we need to be able to damp these functions. This isn't a bridge one. We're going back to question 4, and we've got a current. And, you know, my knowledge of electricity is minimal at best. It's bad to touch things if they zap you. That's about the extent of it. But anyway, the only bit you get in the whole book is just this brief little statement here, and there's a little bit earlier in the book, but I, of course, don't have a copy of the book electronically at home, so I'm just going with what I can remember here. But the charge, we can find the charge in a system by finding the integral of the current. Great. Here they gave us a current equation. We did this in class. We subbed in 3, got that first bit. That was no worries. All right, so we're going to go ahead now and find the charge in the system when t equals 5. We knew that the initial charge was 100. Initial charge of 100. And this is where we went a couple of different ways. So I started off by saying, well, why don't we just go ahead and find the integral, because it says that's what we have to do. So we started off with if the integral equals dq dt, and doing the right thing here, separating our infinitesimals like that, integrating each side, and we end up with q is equal to the integral of whatever I was, and I was, of course, 20e to the negative 0.2t multiplied by the sine of pi t over 4. Excellent. And it's perfectly good at this stage to go ahead and do it as an indefinite integral, find the value of c, and then what you come up with is an equation for the charge at any time t. If I go ahead and solve that, that's what I'm finding. I'm finding an equation for the charge at any time t. Sub in 5, it'll give me the charge at the time of 5. So that's the way I started. Now you remember Mr. Canalese said, oh, we've got to integrate from 0 to 5. And he's actually right. That's a perfectly acceptable way of doing it as well. We could just do the definite integral over that time period. what the integral of I dt between 0 and 5, the definite integral, is going to give us, that's going to give us the charge in the circuit, the total charge in that circuit, or change in charge in that circuit over that period of time. Okay, so it's giving us the charge over that period of time. If we then add that to the initial charge, we end up with the same answer. So doing it this first way, where you do the indefinite integral, sub in 5 later, or doing the definite integral and adding on 100, give you the same answer. It doesn't matter which way we do it. I think we should try and do it both ways, just so that you can see that that's what happens. Now, another interesting thing I thought we'd do, always handy to sketch these things. Here's the equation sketched there. What we're doing is we're going all the way up to 5, which is about here somewhere, and we're going to integrate that area from 0 to 5. So you see it's actually going to increase the charge, and then it's going to decrease a little bit. I don't understand how these things work. What actually happens is, if we are charging, apparently there's a capacitor there storing the charge. Who knew that? Lots of you, not me. That's what the C stands for in that. I think it said LCR, because I'm sure Niall told us it was a light cavalry regiment. But everywhere else I seemed to look when I was having a look at what actually circuits do. I think they called them CLR or LRC, so I don't know whether that means it's a different sort of circuit. I don't know, but at any rate, enough of that. The integral, you can see, is going to increase, and then it actually discharges a little bit. Apparently, as something's charging, the capacitor can discharge as well. So there you go. You learn something new every day, and that's part of the fun of maths. Excellent. So anyway, if we wanted to integrate that, Desmos draws it beautifully. Doesn't find the integral for us. Your calculator will, though. So here I have the function entered in there. If I wanted to find the definite integral, your calculator's good at definite integrals. So let's have a look and see what happens if I do the definite integral of that. Oh, there's one I prepared earlier. I don't know why it's doing that. Let's just do it again. We'll G-solve for the definite integral. And we want to go from 0 to 5. Oh, look, it's 31.72. If we add that to the initial charge of 100, we've got 131.72. Exactly the right answer. So doing it on your calculator, easy. It's good for you in an exam because you know you can get the right answer and you know if you've made a mistake. And then you either leave it and say, this is not the right answer because when I checked on the calculator, do this quick sketch, this is the answer I should have got. Great. You've acknowledged there's a limitation with your solution. There must be an answer somewhere. If you've got the time, go ahead and try and fix it then. If you don't have the time, go and do other questions. You're still going to get most of the marks for that question anyway. Go and finish your other questions, and then if you have time at the end, come back to it. Don't get stuck on one question and spend the next 40 minutes looking for your answer. It's probably a minus sign somewhere that you forgot to change or included an I bit or not an I bit. It's going to be something annoying like that. Get it your maximum amount of marks, value for the time you're putting in, and move on. Come back to it if you've got time. So there we go. We know it's going to work with a definite integral, but let's go ahead and look at how we did it with the algebra. So this is going to take a little bit more work, but that's okay, because we're not afraid of that. Random mark all over it there. All right, so integral of 20 e to the negative 0.2t. And what are we going to do with this sine pi on pi t over 4? We will remember sine pi t over 4 is the imaginary part, if I'm using Euler's form, of e to the pi t over 4 I. E to the I theta. I put the theta in front of the I. It doesn't really matter, does it? It's the imaginary part of that. So, oh, good. When I'm doing this integral, I know that q equals this. So q, another way I could think of it, it's the imaginary part of the integral of 20 e to the negative 0.2t. I can see I've left out a little bit there, haven't I? I got excited and wrote it over on the side, the substitution we're going to make, but I didn't actually keep it there. There it is, sine of pi t over 4 dt. Sorry about that. It's good for you to see this is how maths works. No one just gets to an exam, sees a question, writes out every answer perfectly. Doesn't work that way. It takes a little bit of thinking. You've got to think about what you're doing. Go back and check. Make sure at each stage that it makes sense what you've done. I could see I'd forgotten that, so I knew to go back and put it back in. All right, so now we're wanting the imaginary part of this, and the other bit is then going to be e to the pi t over 4I dt. Great, because I'm really good at integrating e to the power of something. But before I do, I'm going to put that little 20 out the front, and I'm going to make that look a little bit prettier as well, aren't I? I'm going to have e to the t outside of pi on 4I minus 0.2. Let's make that 1/5. It's going to be a lot nicer to work with later on. You don't have to. You can keep with the decimals. I'm a bit like Sequoia. I think I heard someone saying he doesn't like decimals. I can't stand them either. So let's go with those nice fractions. It's going to make our lives easier, and it's going to be much easier to simplify later on. Beautiful. Okay, what are we going to do from here? 20, we can do our integral. So the integral is e t pi on 4I minus 1/5 divided by, remember we're just doing our chain rule, we would have to divide by that so that when we differentiate it, it would cancel out. So this is just going to be pi over 4I minus 1/5. I'm doing an indefinite integral, so I'll whack a little plus c on here. It's really not going to be a problem. Q, the imaginary part of this, well, two things I've got to do. I'm going to have to fix up this by multiplying by the conjugate. In class I remembered to leave room. Here I did not. Let's just fix that up and put that little conjugate in there now. Multiplied by pi I over 4 plus 1/5. Pi I over 4 plus 1/5. There we go. Now I'll put my plus c after that. You can do it on another line, but I don't want to take up too much space here. Pretty good. So from here, I've still got the imaginary part when I'm finding this Q. That's okay. 20 bracket. I was going to do bracket and put the other bit in first. I don't need to. Let's just leave the e there first. Et pi I over 4 minus 1/5. That's all in the power. This is back on the same level as the e and the 20. It's a little bit hard to do with my limited skills. This tablet, I can't actually see what I'm writing. I have to watch the screen while I do it. That's why I look a little bit funny in the camera. But I think the camera still adds something you can see when I'm talking to you. And I'll give you a nice smile like that. So isn't that good? Down the bottom here, what am I going to do? I'm going to use my favourite rule in maths. See, that will make me smile. Favourite rule in maths. Got to love it. Difference of two squares. Pi squared over 16. I squared is going to be -1. So it's going to be negative pi squared over 16. Negative 1/5 by 1/5 minus 1 over 25. Yeah, it's not so bad, is it? Good. All right. Now, I said we were going to do something nice with these, and I think it's probably time to do it. You can see it's not very pretty, is it? You know, negative pi squared over 16 minus 1 over 25, fractions in a denominator. So we've got a fraction within a fraction. It's really ugly. Is there an easy way to get rid of 16 and 25 in just one simple, easy step? Of course there is. What are you going to do? You're going to multiply through by whatever the common denominator is. Well, 25, 16, so what would that be? 400? If I multiply through by 400, I think it's going to be a lot nicer. What do you reckon? Let's give it a go. You'll see why it's a lot nicer if we just have a look. So I'm going to multiply the top and bottom of that fraction. Right here I'm going to go by 400 over 400 on the bottom. So I'm multiplying the top and bottom by 400. You get the idea. Why am I doing that? Because it's going to make my life easier in the long run. And maths is to make your life easy. That's why we have maths. Oh, 8,000, that's good. But oh, look, then I could put 20 into that. And that's going to sort out the 5 and the 4 as well. Do we want to do that? I don't know, I won't do everything at once. Might get a little bit confusing. Oh, I think that's actually got the hand motion there. There you go. E to the T. Yes, I do talk to myself a fair bit while I'm doing maths. It might distract you a little bit. You can always turn the sound down. It won't kill you to have me muttering away as I'm doing this, though. And I think it's actually really important that you hear what I'm thinking. That's why I actually do it. It's important you hear what are the thought processes behind doing these things. Why did I choose to multiply by 400? It's just going to look nicer. It's going to give me integers rather than fractions. Who's better with integers? All of us. Yes, I love fractions as opposed to decimals. I much prefer integers to both of them. So let's sort this out. So when I go 400 by 16, how many 16s were there? Oh, there were 25, weren't there? So that was pretty obvious. Should have made it negative 400 over 400. Doesn't matter now. All right, so it's going to be negative 25 pi squared here. And then how many 25s were there in 400? Oh, there were 16 because there were 4 and 100, so there's 16. This is just going to be minus 16. It's looking a lot nicer already, isn't it? Okay, we still need to just find our imaginary part. That's what I'm actually trying to do. Can I go ahead and find the imaginary part? Of course we can. To do that, we've got to separate this bit back out. Okay, well, we can cope with that. 8,000 e to the negative 1/5 t, so negative 1/5 t or t over 5. You could leave it as a negative 0.2. Still doesn't really matter, does it? Excuse me while I pause and lubricate. It's been a long day. Good athletics today. Good to see some people out there, Stubbo. Not everyone was there. A couple of shot putters away, maybe a sprinter or two, but that's okay. Not looking at anyone, boys. Still surviving okay. All right, there we go. So 8,000 e to the negative t. So I've done the negative bit. And then we've got the e to the pi I over 4. We want to say what that is in Euler form. What is it again? It's cosine pi t over 4 plus I sine pi t over 4. So we're just taking that e to the pi t over 4i, reversed Euler's form from before, and then I've still got this little bracket here as well, don't I? Pi I over 4 plus 1/5. I've got a plus c at the end, and this is all over negative 25 pi squared take 16. Alright, we can find the imaginary part now. All I'm going to do is I'm going to keep the imaginary bits. I'm going to get rid of the rest. So 8,000 e to the negative t over 5. Which bits are going to be... So I've got that little bit out the front there. Now, when I multiply cos pi t over 4 by pi I over 4, yes, that is going to be an imaginary part, isn't it? So I'm going to have pi over 4 cos pi t over 4. That's an imaginary part. Cosine of pi t over 4 times 1/5. Nope, not going to be imaginary. That's going to be real. Don't need that anymore. Oh, this has got an I in it as well, though, so when I'm doing the next bit in my binomial expansion, that's no good. So the only other bit I need is this I sine pi t over 4 times 1/5. Oh, that's not so bad, so it's plus 1/5 sine pi t over 4. And, of course, I have my plus c at the end, and I haven't got rid of my denominator yet, so I've still got negative 25 pi squared take 16. This is actually Q of t. That's the charge in the system at any time t. Got a little problem with this c here. We can deal with that in a second, but that's actually good enough to work with. It's a little bit messy. We could neaten it up. What do we like? We don't like this 1/4 and 1/5, do we? What could we do? Well, if we multiplied that bracket by 20, it'd get rid of the 4 and get rid of the 5 and look a little bit nicer. So if you wanted to continue a little bit of panel beating, making things look pretty, I'm going to multiply by 20. What's that mean? I'm going to divide this by 20. It's going to give me 400 out the front there. E to the negative t over 5. Multiplying by 20, the 4 is going to go to 25 times. This will just be 5 pi cos pi t over 4. And then 20 by 1/5, that's going to be 4, plus 4 sine pi t over 4 plus c, all divided by negative 25 pi squared take 16. All right, we're now going to use our little bit of information, the initial value. When t equals 0, q of 0 equals 100. And I could have just said q of 0 equals 100. Who needs to say when t equals 0? That was a bit redundant, wasn't it? I was going to say when t equals 0, the charge is 100, but then I thought of a fast way of saying it anyway. Too bad. I'm just going to leave it there. Oh no, I'll put a line through it because it's going to annoy me now. We're going to use that little bit of information. Q of 0 equals 100. So 100 is going to equal 400 e to the negative 0 over... Oh, good, that's going to go to 1. So that's pretty easy. And what have I got? I've got 5 pi. Cosine of 0. Cosine of 0 is 1, isn't it? Okay, so that's 5 pi. That's nice. Plus 4 sine 0. Sine of 0, that's going to be 0. Excellent. That bit we don't need anymore. And this is just plus c, and this fraction was still over. Negative 25 pi squared take 16. It's actually simplified really nicely because we're working with those nice integers on top and on the bottom. It's just made our lives a little bit easier. Okay, so what's c going to equal? Well, an easy way to do this, if I factor out that negative from the bottom, I'm going to have, what have I got on the top? 2000 pi. 2000 pi, and this is going to be negative 25 pi squared plus 16 if I factor out that negative, plus c. Oh, now that's pretty easy, because then c is just going to be 100. This negative, I could just think of it as being out the front of the whole thing, couldn't I? It's just going to be 100 plus this 2000 pi over 25 pi squared plus 16. Why did I want to know that? Because now I have the equation for the charge at any time. Oh, I touched something on my tablet that looked pretty fancy, didn't it? I must have the touch enabled. It don't usually. No, I'm trying to find where my cursor is. It's actually really interesting. The other program, when you look at it, it's got a nice yellow circle around it. When I'm looking at it, I can't see that. And it makes it really hard sometimes when I'm just in writing mode to find where my cursor is. It's kind of annoying. So if you ever see me looking around and doing something weird, that's actually what I'm doing. All right, so I've got the value of c. So what is the value of my charge any time t? Well, it's just this thing with the c added in. Now, this is the same denominator, isn't it? Remember, this denominator here is just with a negative. So I could actually make the denominator 25 pi squared plus 16 and have this numerator, 2000 pi, minus this expression on the top there, 400 e to the negative t over 5, and then what have I got? 5 pi cos pi t over 4 plus 4 sine pi t over 4. Oh, come on, I'm running out of it. Don't do that to me. Excuse me, sneaking it in there. I could just come down here and drag it across, but it's kind of annoying to do that. So that's that bit. This is all over 25 pi squared plus 16, but we still haven't got this 100 there, do we? So I now need to add 100. Okay, we want to know the total charge in the system when the time equals 5. Okay, well that's not going to be too hard to find. 2000 pi, that's not going to change. Denominator is not going to change. 25 pi squared plus 16 plus 100 doesn't change. What do we have to do here? Negative 400. Oh, okay, it's going to be negative 400 e to the negative 1, because 5 over 5 is going to be 1 and it's a negative, so negative 5 over 5. Okay, that's not so bad. 5 pi cosine of 5 pi over 4. Let's get our best friend in maths out just to check. 1, 2, 3, 4 quarters. 5 pi over 4 is going to be in the third quadrant. Cosine is going to be negative there. You can also remember ASTC, negative in that quadrant. And what is the cosine, or the sine indeed, of pi over 4? That's the wrong triangle. How can I say it's the wrong triangle? I didn't even draw a triangle, did I? But I could tell I just didn't draw it at an angle that was going to make it feel right. I wanted to draw closer to a 45-degree angle, or a pi over 4. What am I even using degrees for? You're big kids now. Let's put it back in radians. 1, 1, and root 2. And let's make it look nicer. Pi over 4. Pi over 4. All these things that go running through your brain while you're doing these things. Okay, so the cosine of 5 pi over 4, cosine of pi over 4 is 1 over root 2, which we write as root 2 over 2. So that's just going to be root 2 over 2. And this is negative. Doesn't like it because I'm trying to squeeze in a negative there. That'll do. Negative in there. And then 4 sine 5t over 4. Well, sine is also going to be negative. Remember, sine's your y coordinate. It's also negative. It's going to be negative. So it's going to be minus 4 root 2 over 2, which is just going to be minus 2 root 2. So see what happened there? The 4, I'm going to multiply that by negative root 2 on 2. The 2 cancels with the 4, and I get negative 2 root 2 plus 100 over 25 pi plus 16. Okay, the plus 100 was separate. It's not over that. You get the idea, and I didn't close my bracket off. Well, it's a little bit ugly. Let's go. I could use my calculator, but I think Desmos is going to just type it more nicely for me. I don't want to get rid of that one just yet. So what on earth did I have then? I had in on the top, we need the 2000. Why is it doing that? Bracket 2000 pi. Was there a pi? Yep, minus 400 e to the negative 1. Just push across, and then I've got brackets. Negative 5 pi root 2 over 2. Oh, all the way to there. That's where I want to be. And then it was minus 2 root 2. Here we just type SQRT2. You'll see that that works nicely. And after all of that, well, it's added in its own things. I needed to add 100, didn't I? Oh, but I didn't divide all of this. So I have to go back to that fraction and divide the whole lot by 25 pi squared plus 16. Look at that value, 131.71894, blah, 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 blah. That's the number we wanted, wasn't it? That's the number we got when we did it on our graphics calculator. When we add 100 to that, we get the same thing. You beauty. It works doing it that way. It's not a problem. Works beautifully. We can see the definite integral from 0 to 5 is also going to work the same way. When I was saying in class, well, it doesn't matter whether I include the C or not, the definite integral, why are they making us do that? I was right. We don't need to. So if you go ahead and you do the definite integral, your working is going to look the same. What's going to be different? You just never write this plus C. When you get to this line here, so far I haven't done anything. All I do at that stage, so when I'm doing the definite integral, let's see if I can snip this out. All of the working is the same to that point. So if you're doing it the definite integral way, I can just go to there. I was wondering about scrolling down and putting it elsewhere, but I'll just go to there and I'll put it in. We'll slide across here. You'll be able to look at it still. I need to go a little bit further if I can. Alright, so when I do this, when I'm doing the definite integral, which is what I was talking about, hold my pen the right way around, and I'll be able to draw with it again. There we go. So this time it's the integral from 0 to 5. That's the charge over the first 5 seconds. So I can't call this q at time t because now I'm just doing the definite integral. So this is the value of the definite integral. Of course, because I chose to snip that as a photo, it's not going to let me erase it, so we'll just cheat and do it like that. If we do this, we're going to get the same answer. Let's see, we're going to have 400 e to the negative 1. This thing we sorted out before, didn't we? What was it? It was negative 5 pi root 2, and this was minus 2 root 2. This is all over negative 25 pi squared takes 16, plus 16, because I'm factorising that negative out. Okay, that's okay, so it's that thing. And I'm going to subtract the same thing when I sub in 0. So what was that? That was going to be 400 e to the negative. What happened there? Really got to turn the touch off on this thing. It's going to keep doing that. But maybe it entertains you watching me struggle. I hope you're enjoying this massively long recording too. You know you can double the speed. Hopefully you figured that out before now. 400 e to the 0 is 1. I'll put that in there just in case you come and look at it and go, where did that e go? I'm putting it in here. Cosine of 0 is 1. Okay, so that's good. So that's going to be 5 pi. The sine of 0 is 0. So that's all I'm going to have for that bit there. And again, this is over negative 25 pi squared plus 16. And you will very quickly realize that this is my 2000 pi, and minus the negative is going to be positive, so I'm going to have 2000 pi. I can now write the 25 pi squared plus 16 as a positive denominator. What's left on this bit? It's going to be, so I'm subtracting this because you can see that negative could go all the way out the front of that whole fraction there, or I could actually cancel with the negatives in that, take a negative out of this one and the bottom one, so I could just have plus 400 e to the negative 1. I'm going to have 5 pi root 2 plus 2 root 2, which I could factor the root 2 out of. What is that equal to when we figure that out? Alright, let's see if I can do this in a little bit of a smarter way. That looks a little bit nicer, doesn't it? Oh my goodness, look at all those videos. You don't want to see all of those. Let's make it look like that. Too many there. 2000 pi plus 400 e to the power of negative 1. Go away. Oh, okay. Giving me a subscript. How annoying. That's better. 5 pi plus 2 root 2. All of that. No, not some of it. All of it being divided by 25 pi squared plus 16. And now it's misbehaving and giving me 37.93. Why has it gone and done that? 2000 pi. Yeah, that's right. That's what I get when I sub 0 into that whole thing, is it? I get 400 times 1 times 5 pi. Yep, 2000 pi over the denominator. Okay. What happened when I subbed in 5? I get e to the negative 1, 400 e to the negative 1, minus 5 pi root 2, minus 2 root 2. So if I take out negative root 2, I get 5 pi plus 2. Is that what I typed in? 2000 pi plus 400 e to the negative 1, 5 pi plus 2 root 2. And it gives you the same answer, yet somehow didn't. That's a bit dodgy, isn't it? Alright, well, I'm going to pause for a second and find my mistake. You can enjoy not watching me do that. Actually didn't take me very long at all, which is nice for a change. All I've done is where I've gone up here and said this was root 2 over 2, I've run the root 2, and what is missing? The over 2, isn't it? That's all that was missing. I just forgot to write the over 2 when I said it. What does that mean when we go and calculate it over here? I knew we were doing something right. That's 5 pi if I just made that over 2. So I've still factored out the root 2, which is fine. If I put that over 2, I'm now getting the 31.712. So the increase in charge, did I say 712? 72 or 7189, blah, blah, blah. Let's not pretend I'm finishing it. Therefore, the total charge is the initial charge plus 31.7189, which is 131.7189. I said point. I better put it in there for you. There you go. Both methods work. They work the same. What's wrong with this question? There's a few things. One, they didn't really explain much about circuits, so it was a little bit confusing for those of us who had no idea what they were. 2, an initial charge of 100. 100 anythings? 100 teaspoons? No units means it's a little bit vague and not very valid. That would bother someone trying to apply their maths. We can just cope with whatever the units were. We can go ahead and find the number. Not very useful, but we can do it. So we did. Okay. Those two things work the same way. We get the same answer. Which way would I be doing it? I actually think, the last one looks easy, but that's because we didn't start doing the work until here. I think in some ways it's easy if you find Q of t first and the C value, use that. Because then if they change the parameters, if they say, well, what was the charge at 7? What was the change in charge? Rather than having to go back and do the integral again, you can just say what it is. Remember though, use your calculator to check what values you should be getting, so you know if you're getting it right or not. That's what enabled me to identify that I'd left out the over 2, just in that example that we did then, that little over 2 right there. So, hopefully that clears it up a little bit. It was a long video. Usually I try to keep my videos 5 to 10 minutes. A lot of explaining in that one, plus doing it twice. If we did it once, if we didn't get distracted by the beautiful song that we had, it would have been a little bit faster. I hope that helped and it clears up a few things. I'm going to upload it and send it to you. I will be chatting with you guys again whenever we next have maths, and we'll do a couple more of these. Don't let them scare you. They're not so bad. It's good practice. Maybe if I feel inspired, it's already tomorrow morning in my head. If I'm feeling inspired, I might do it doing the integration by parts, but as Jack said, he did it and it just made a mess anyway. Sine and cosine ones are a little bit of a pain. You've got to do a few steps. I don't think this is too bad. I enjoy multiplying by my conjugate. I think you'll find if you've got fractions over fractions, find the common denominator, multiply through by that. That helps a little bit too, just to neaten it up. And I find not substituting in or touching my calculator to the end to be really helpful. You might find otherwise. I don't know. Alright, I think we're done. Have fun, guys. I'm going to figure out how to turn this off.